Good morning, students. Our next theorem is based on bounded linear operators. So the theorem is, we have three bounded linear operators. First bounded linear operator is T2 from the norm space X into the norm space Y. Second, T1 from the norm space Y into the norm space Z. And third is T from the norm space X into itself. Then we are to prove that norm of the composite of T1 and T2, that is less than or equal to norm of T1 into norm of T2. And in the second part, we prove that norm of T raised to the power n is less than or equal to norm of T whole raised to the power n. Here, this n is a natural number. So in order to prove the first part, first of all, let us prove that the composite of T1 and T2, that is a linear operator. Now, T2 is operator from X into Y and T1 is operator from Y into Z. So, T1, T2, that is an operator from X into Z. Now, to prove that this operator is linear operator, let us take two vectors x1 and x2 belonging to the norm space X and two scalars alpha and beta. Let us find the image of alpha x1 plus beta x2 under the operator T1, T2. Now by definition of composition of T1 and T2, this can be written as T1 of T2 of alpha x1 plus beta x2. Now T2 is linear operator, so by using linearity of operator T2, the image of alpha x1 plus beta x2 under T2, that can be written as alpha into image of x1 under T2 plus beta into image of x2 under T2. Now again, T1 is linear operator, so using linearity of T1 here, this expression is further is equal to alpha into image of x1 under T1, T2 plus beta into image of x2 under T1, T2. So this proves that the operator T1, T2, that is linear operator. Now next we prove that this operator is bounded operator. So in order to prove it bounded, let us take an element x belonging to the norm space X. And let us consider the norm of image of x under T1, T2. Now because T1 is bounded linear operator, so this can further be written as T1 T2 x norm is less than or equal to norm of T1 into norm of T2x. T2 is also bounded, so norm of T2x is less than or equal to norm of T2 into norm of x. So this proves that the operator T1 T2 is bounded operator. Now for all the non-zero x, from here we get norm of T1 T2x divided by x norm is less than or equal to norm of T1 into norm of T2. Now let us take supremum over all the non-zero elements of the domain of the operator T1 T2. So by definition, this will become norm of T1 T2. So we get norm of T1 T2 is less than or equal to norm of T1 into norm of T2. Now next we prove that norm of T raised to the power n is less than or equal to norm of T whole raised to the power n. We prove this result by induction. So let us take T1 and T2 replaced by T in the first result. So for this will become norm of T square less than or equal to norm of T whole square. So this proves the result for n is equal to 2. Now let us suppose as an induction step, the result is true for n is equal to k. It means norm of T raised to the power k is less than or equal to norm of T whole raised to the power k. Now we prove the result for n is equal to k plus 1. So let us find the norm of T raised to the power k plus 1. Now T raised to the power k plus 1 can be written as t raised to the power k into t. Now again using this, that will be less than or equal to norm of t raised to the power k into norm of t. Now using the induction step, this is less than or equal to norm of t whole raised to the power k. So we get norm of t raised to the power k plus 1 is less than or equal to norm of t whole raised to the power k plus 1. So this completes the induction, and hence we can say that by principle of mathematical induction, the result is true for every natural number n. So we can say that norm of t raised to the power n is less than or equal to norm of t whole raised to the power n, and this completes the proof. Now next we define what are equal operators. So let us take two operators t1 and t2. We say that these two operators are equal if these two conditions are satisfied. First condition, their domains are same, means domain of operator t1 is same as domain of operator t2. And the next condition is the image of every element of the domain under the two operators, that should be same. It means image of x under t1 is equal to image of x under t2, where this x belongs to the domain of t1, or we can say domain of t2, because both domains are same. Next we define restriction of an operator. Let us take an operator t from dt into y. Then the restriction of this operator t to a subset of dt is denoted by restriction of t to the set B. This is an operator from B into Y, and under this restriction, the image of every element of B is same as the image of that element under T. So we can say that for every x belonging to B, the image of x under restriction is same as image of x under T. This mapping T and with restricted to B is the restriction of operator T. Now let us define extension of an operator. So let us take the operator T from dt into y. Then the extension of this operator T to a set M. This M is superset of dt, means that contains dt. This is a mapping denoted by T bar. This is a mapping from M into Y, such that the image of every element of domain of T under the mapping T bar is same as the image of that element under T. So we can say that T bar x is equal to Tx, and this should be true for every element of domain of T. Here we can say that T is the restriction of T bar, or we can say that T bar is extension of T. Now next there is a theorem based on this definition of extension of T, which is bounded linear extension. So the theorem is, let T from dt into y be a bounded linear operator. Here dt is a subset of norm space X, and this y, that is a Banach space. Then we are to prove that T has an extension T bar from closure of dt into y. Here this T bar is bounded linear operator such that the norm of T bar is same as the norm of T. So in order to prove this, let us take an element belonging to closure of dt. It means X is closure point of domain T. So by definition of closure point, there exists a sequence, say xn, in the domain of T such that the sequence xn converges to X. Now let us find norm of Txn minus Txm. Now T is linear operator, so T of xn minus T of xm, that can be written as T of xn minus xm. Now also T is bounded operator, so by boundedness of T, this will be further less than or equal to norm of t into norm of xn minus xm. Now, because the sequence xn is convergent sequence and therefore it is a Cauchy sequence, so by definition of Cauchy, as n and m approaches to infinity, the norm of xn minus xm approaches to 0. So we can say that norm of txn minus txm approaches to 0 as m and n approaches to infinity. So by definition, we can say that the sequence txn, that is a Cauchy sequence in Y, but Y is Banach space, it means that is complete norm space. Therefore, every Cauchy sequence in Y will be convergent in Y. So this sequence T of xn, that is convergent in Y, and let us take this converges to this element Y, which belongs to the Banach space Y. Now, by using this Y, let us define T bar. Defined by T bar of x is equal to Y. Now we show that this definition is independent of particular choice of the sequence in domain of T, which converges to x. So let us take two sequences, sequence xn and sequence zn in the domain of T, such that both sequences converges to x. And let us define a sequence Vm having the elements, first element x1, then z1, then x2, then z2, and so on in this way. Now, because the sequence xn converges to x and the sequence zn also converges to x, therefore the sequence Vm, that will also converge to x. Now, because T is bounded linear operator and the sequence Vm converges to x, and under a bounded linear operator, the image of Vm will converge to image of x. So we can say that T of Vm, that is also a convergent sequence and that converges to T of x. And also we know that subsequence of convergent sequences also converges to same limit. So therefore, the subsequences of T of Vm will also converges to T of x. The subsequences of this sequence are T of Zn and T of Xn. So they will also converge to the same limit as the original sequence T of Vm. So we can say that the operator T bar, that is uniquely defined at every x belonging to closure of dt. And also T bar is linear operator because for every two elements x1 and x2 belonging to closure of dt and the scalars alpha and beta, we have the image of alpha x1 plus beta x2 under T bar is equal to alpha into image of x1 under T bar plus beta into image of x2 under T bar. And also image of x under T bar is same as image of x under T for every x belonging to domain of T. So we can say that T bar is an extension of T. Now next we prove that the norm of T bar is equal to norm of T. So let us find the norm of image of x under T bar. Now image of x under T bar, that is denoted by y. So this becomes y norm. Now y is the limit of the sequence Txn as n approaches to infinity. And this can further be written as limit n approaches to infinity of norm of Txn. Now T is bounded linear operator. So this will be further less than or equal to norm of T into norm of Xn. And from here, norm of T bar x is less than or equal to norm of T into limit of norm of Xn. So this becomes norm of T into norm of x. So we get norm of T bar x less than or equal to norm of T into norm of x. And this proves that T bar is bounded. And also for non-zero x, from here we get T bar x norm divided by x norm is less than or equal to T norm. Now taking supremum over all the non-zero elements of domain of T bar. So that will become the norm of T bar, and this is norm of T. So we get norm of T bar is less than or equal to norm of T, and also the norm of T bar is greater than or equal to norm of T, because T bar, that is an extension of T, and the norm defined by supremum cannot decrease in an extension. So combining these two, we get norm of T bar is equal to norm of T, and this completes the proof of the theorem, and this also completes your section 1.